All right, the old Panda 3D scene graph. Most of us are familiar with it. And we all know that a scene graph looks like this. The archetypal scene graph. Let's see. In Panda, the scene graph is made up of Panda nodes. Normally we don't deal with the nodes directly, we deal with node paths more commonly. But the node path is a handle to a node. The majority of nodes in the scene graph are of type Panda node, but there are certain nodes that are some specialized type. And it's these specialized type that have the interesting bits in the scene graph. And in particular, you're likely to find a geom node down at the leaves, because the geom node is a type of node that actually has the geometry, the vertices and stuff that actually get rendered. Virtually everything that Panda can render is stuffed in the geom node somewhere. The other stuff, just regular Panda nodes, are just the glue that holds the geom nodes together. So in principle, you could just build up your scene entirely of geom nodes, and they could all just be stuck at the root of the graph. And then you wouldn't have a scene graph, you just have a scene list, which works. There are graph extensions that work that way as well. But the hierarchical graph gives you a lot of power. So let's see. In particular, well, let me get into some of the more fancy stuff in a minute. But let me talk about the node path, because we deal with node paths a lot. We have invented this concept of a node path since back in the day, and the thing we mainly use a node path for is just as a handle to a Panda node, so that we can collect all the common interfaces and all the standard nodes together. Every kind of Panda node has certain things that you can do to it. You can set a list of attributes on the node. You can set a transform on the node. You can change its children, change its parents. And these are the things that you can also do with the node path interface. But that's not good enough reason by itself to create this whole other class. I mean, we could have just added these basic interfaces on Panda node. In fact, most of them are in a more primitive form. The reason we added the node path class was to handle one particular complexity, which is instancing, which is rarely used and rarely recommended, but there are times when instancing is very useful and necessary. And for that reason alone, we invented the node path class. And let me talk about what instancing means. Normally, if your graph looks like this, this is technically just a tree, because everything has just one parent, and some nodes have multiple children, some have no children. But you might do something like this, where now this node has multiple parents and therefore appears multiple times in the scene graph. And now you've changed this tree from a graph. I mean, changed this from a tree into a graph. And now this node, by virtue of having multiple parents, gets rendered twice during the traversal. And I'll talk about the render traversal in a little bit. But basically, this means this node shows up twice. So effectively, it's as if we duplicated the node here, where this is the same node here and this is the same node here. Because we've got this node in two different places, we need to have a handle to the node that's not just related to the node itself. If we do operations on this node, it'll affect both of these. Sometimes we want to do an operation that affects only one of these copies. For instance, we might want to take this other copy and move it to this other node over here. We want to change this link and this link only to move over to this node, but we don't affect this link. Or if we draw it back like this, we want to take just this link and move it from this node to that node. And for that reason, we have the node path class. Once we have a node path handled to a node, the node path itself contains a full path of from the child node all the way up to the root. That's the sense of the name. And thus, each node path is unique. So we have a different node path that refers to this path, and one node path that refers to this path. The same node, and certain things that we do on the node are going to affect the same node in both cases. But other operations, like reparenting, only affects one of the instances, and that's why we need to have the node path class so we can do that. There are other things that we do in node path, but I'll get to those in a little bit.
instancing
is very powerful, as I said, but it can get you in trouble. Because what happens is, maybe partly because we have this node path interface, which makes it look like there are two different nodes, we've got two different handles to the thing, you tend to forget that they're actually the same node. So if we have this guy who is a child of this node, and this same guy who is also a child of this node, they have the same children, and if we do any operations down here, like reparenting these children down here, or changing the transforms, or changing the state, or any of these things, it's going to affect both of them, which causes problems if we're not expecting it. And this has caused problems in the past. It causes problems all the time with naive users. So this is one of the main reasons why we recommend not using instancing unless there's a real good reason for it. If you want to have this node appear twice in scene graph, well, you can just use copy to, which is going to create a brand new copy and all of its children to the new place. This is much safer because now we've got two different handles to two different nodes, and if we do any operations on these other nodes, it's only going to affect these other nodes. So we don't accidentally change things in the model pool or in some other storage place or multiple copies of the thing all over the place if we don't mean to. Now, fortunately, they have almost the same interface. If you have a node path, you can say node path.instance2. This interface takes your existing node path and creates a new instance of it, which means it just reparents the node path, the same node into the scene graph in another place under this other node that you indicate. And that would be meaning if I call it on this node and reparent to here, that creates this arc here. The return value of this call is the new instance. So normally you would say b equals node path instance to new parent. This is almost the same as b equals node path copy to. Very similar interface, very similar function, except that with copy to, instead of just creating a new arc, we duplicate the whole hierarchy down there. And also remarkably similar to node path.reparent to. This is, of course, the interface that we use all the time, and reparent to simply means remove this existing arc and move it to this other arc. Reparent to doesn't need to return anything because it's operating on the node path in place, but instance2 and copy to both return the new instance or copy. Now, a lot of people resist copy to because they feel this is wastefully duplicating all these nodes. Why should I waste all that memory when really I'm not going to modify these things? I just want to have another copy of this thing, and I promise not to change it. So I'd rather use instance2. But in fact, copy to is relatively inexpensive because the only thing it copies are the nodes themselves. If there are any nodes in the leaves that have actual data within them, such as geom nodes, which might have thousands of vertices, large tables of things, characters with lots of animation tables, all those are copied, the data itself is copied by reference. So you end up with two different nodes down here at the leaves, different node objects, but the internal structure within the nodes are the same. So there's not a lot of waste. There's just the duplication of the node structures themselves, which is relatively lightweight. It's not free. It's true, there is some cost to it. So there are times when really you really do want an instance, and that's the right thing to do. Especially, classic example is a flight simulator programming thousands of trees. I don't know if you're really going to put thousands of tree models in your scene graph, but if you do, instancing might be the way to do it. Let's see. There's one other minor trick that's sometimes people don't know about. It's kind of handy. You can also do nodepath.instance2 empty node path. You can create an empty node path on the fly like this. An empty node path normally isn't used for very much at all. It's a node path that has no nodes at all in it. It's just an empty handle. Most of the time, if you got an empty node path, it's an error. It gets returned from find or load model or things like that return a node path. Empty node path usually means there's something that wasn't there that expected to be there. But in some cases like node path instance to new empty node path, what that means is take my node and reparent it or create a new instance to nothing. Which just means you've got a new instance of the node, which believes it's at the root of its own scene graph. And that's kind of silly. except that now you can take this instance to and reparent it to something else. Well, not the same node, but to another node. And so this is a kind of a shortcut way to, if you follow this up with node path reparent to the old parent, you've got a new instance. And so if your intention is to create a new instance, you can do it without necessarily attaching it to a node right away. This sort of just declares your intention to create a new instance, and eventually when you do attach it, it will be a separate instance. Similar with copy to. If you node path copy to an empty node path, it gives you a brand new copy of that node and all of its children. The other common thing that we do, most frequently common thing, is showing and hiding and stashing. A lot of people are initially confused about the difference between stash and hide because they are very similar in function. Internally, they're very different. It's worth pointing out what the difference is. When I take a node, on any particular node, I can call show or hide. And of course, that just makes the node stop being rendered. But all it does is it puts an indication on the node that the node is hidden if I call node.hide. The node is still attached in the scene graph. Any operations that I do on the node will find it. The node still contributes to its parent's bounding volume, and collisions will still traverse through it. Most other things are still applying to the node except for rendering. If I'm rendering the scene, the render traversor just stops right there and doesn't traverse any further. This also means that I hide all of the children underneath the node. Stash, you can think of it as actually removing this arc so that the node is no longer in the scene graph, although it's not exactly what it's doing either. It's actually moving the arc into a special place where it still remembers that the arc is actually there, so that you can call unstash later. And when you unstash it, it returns to where it was in the scene graph. So stash is often used in lieu of reparent to nothing because it allows you don't have to keep track of where it's supposed to be when you want to unstash it. Now that has cascading effects. When you stash a node, remove it from the scene graph, suddenly it's no longer a child of this node, which means the bounding volume is no longer there. So it has to recompute the bounding volume for this node and all above. It also means that collision traversals and other kinds of traversals never visit this node at all. It's simply not there anymore. If I try to find the node, I'm not going to find it. If I write the BAM file out from here, it's not going to be written out. Anything that I do on this node and traversing down is just not going to find it. There are a few exceptions because, remember, it actually does know that it's there. And you can ask this node what its stashed children are, and it will tell you. And there are funny features on find where you can tell it to find stashed nodes as well as regular nodes, and then it'll show up. But you have to know that you're looking for a stashed node. When I hide a node, I lied a little bit when I said that it hides all the children below it and you can never see them again, because there's actually a new feature, a relatively new feature in Panda where you can say, well, really, I want to show this node even though its parent is hidden. And that's called show through. And what that does is it puts a new indication on this node, which gets propagated up through some clever bitmask tricks, so that when I come to this node, and it actually does render, skip over this node, and visit this node. Show through is a pretty handy feature to address the inconvenience of hide. It is kind of inconvenient when you hide a node and suddenly you can't see any of the children below it. If you want to hide a node but show one of its children, you either have to reparent the children out of under there, or you have to go and hide all the leaves of the node. Show through allows us to fairly efficiently work around that problem, and we use that to advantage in many cases. For instance, in Pirates, when we're rendering the shadow render, we want to render only the avatars, and the rest of the world we don't want to render at all. So what we do is we put a hide at the top of the scene graph, and then we do a show through on each of the avatars. That very efficiently makes it traversal visit only the avatar nodes. It can immediately prune out everything that's not an avatar. It works out pretty well. There are also options on show and hide. Yes?
What happens to show throughs for children?
Shown
as well?
Yes, they are shown as well. And you can explicitly hide them again. There's also a fancy feature with show and hide that allows you to do this operation per camera. And this does get used occasionally. The way this works is per bit mask, you can set up a unique bit per camera, and then when you call show or hide, you pass a bit mask, an optional bit mask to those functions. And that specifies the cameras that you want this operation to apply to. As long as each camera has a unique bit, that works out pretty well. But it's up to you to set up a unique bit for each camera. By default, I think every camera has all bits on. So you have to pick one bit for each camera and set that one for each camera. Then you have to keep track of all that. But all that's true, that applies to show, hide, and show through. Now none of that works for stash. Of course, if you stash it, it's gone. Sorry, you're not getting the children.
An example is jungle vines where we use that trick, or the camera.
Yes, that's a good example. In Toontown, there's the mini game with the jungle vines. We have two different cameras viewing that. There's the main camera where the avatar is playing the game, and then there's a little map view. Map view sees the same scene graph, but it wants to see different things. So we use show and hide on that. Similar example with the shadows and pirates that I mentioned. The way we achieve the render only the avatars in the shadow camera is to have a special bit for the shadow camera. Okay. The next most common thing we probably do in the scene graph is updating the state. This might be more common than hiding and showing. I mean, updating the transform. The transform is very frequently changed. It's, of course, you think of it as a physical location in the graph. Typically, it's just a position, often a rotation, sometimes a scale, and some more esoteric transforms. But the transform itself includes the aggregate of all these operations. And it's basically anything you can store in a 4x4 matrix. The transform object itself is actually more general than a 4x4 matrix in the sense that it remembers whether you stored just a pause, or just a pause in a rotation, or just a rotation scale. It keeps those components separately for purposes of more efficient composition of matrices in certain cases, and more accurate composition of matrices. But at the fundamental case, it can also just store a 4x4 matrix if it has to. A 4x4 matrix is a general representation of pretty much anything you can represent in terms of pause, hyperscale, and skew. And a few more things that you can't represent with those. But it has some disadvantages, particularly in single precision floating point arithmetic, where you can lose precision pretty quickly if you accumulate matrices too often. But in general, when you call set pause blah 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 on a node, or set hipper, what it's doing is it's grabbing an object on the node called a transform state, which accumulates all of these various operations you might do on a node, applying the specified transform to the transform state, and then stuffing the modified transform back onto the node. So every node stores a transform state. And the transform state is, you can think of as a 4x4 matrix. And all these operations more or less operate on that transform state. Let's see. When we traverse the scene graph in order to render, Panda has to start at the top, visit this node. It goes from left to right, depth first traversal, and you can see the order that the nodes are listed in each child. So it starts with the first child, and then goes to all of his children, and goes to all of his children. As it goes, it basically accumulates the transform states, so that this transform state gets multiplied by this one, which gets multiplied by this one, and so on down the line. When we finally reach a geom node, wherever there might be a geom node in the scene graph, we take the transform that we've accumulated to that point and apply that to the vertices for rendering. Incidentally, even the Panda nodes that you have never called set pause or set hipper on, they do have a transform state also. They always just have the identity transform state. And the transform state class has some features where it short circuits the identity case. So when you call transform state.compose to identity transforms at early outset, it doesn't actually have to perform the matrix multiply. Transform state also has some stuff built into it to cache the operation. So when you call transform state compose A and B with two transform states, that's a relatively expensive operation. It has to do a bunch of adds and multiplies to multiply the matrices. So it'd be nice if the next time we call the same operation, it would cache that. And it does, and I'll talk about how that works in a little bit. But for now, just understand that fundamentally, as we traverse a graph, we have to do all these multiplies of all the transforms to get to each answer at the leaf. And that's the way to think about it as you're programming. Fundamentally, you just realize, you start to think about, as I transform this node, it's also transforming all the children. So you can think of changing a node's position or rotation relative to its own parent, which is what we commonly do. That makes each node is basically a coordinate frame. And there are classic examples of coordinate frames for visualization exercises. A man on a train, walking from one end of the train to the other. Train's moving 60 miles an hour. Man walks 3 miles an hour. Depending on which way he's walking in the train, he's either walking 57 miles an hour or 63 miles an hour. And you can think of the train as being one coordinate frame and the man as being parented to that train. Once you get your head around that mindset, it works out pretty well. The other thing that's very useful to do with a scene graph, and that Panda lets you do very easily, is ask those aggregate questions to do that arithmetic right away. If you ask the man what his position is, you get one answer relative to his parent. But what you really want to know maybe is what is his position relative to the train tracks. And so this is where Panda's scene graph is quite powerful. Of course, you can call nodepath.getPos with no parameters, we all know this, which returns the position that we set on the particular node. We can also call nodepath.getPos with any particular node we like. Frequently, for instance, the root of the graph, render, or empty node path is the same thing. GetPos to the top of the graph means get me the position of this node relative to this particular node, or render as this case may be. Which means, really, accumulate this transform from here to here to here, and give me that answer. And that's pretty powerful. Furthermore, it doesn't have to be strictly linear. We could ask, what is this node's position relative to this node over here? That's where it gets really crazy. Because if we got a transform on this guy and a transform on this guy, what we really want to do is invert this transform, go back up here, inverting any other transforms, then reapply this transform and reapply this transform. And of course, it can go ad infinitum. Whatever, pick any node you like, and we can do that operation relative to this node. And again, it seems like it might be a relatively expensive operation, especially if performing all these compositions and at least one inverse. But Panda does have mechanisms to cache that, so it's not quite so bad as it could be. And the other thing that we do that we like a lot, of course, we can set pos with no relative nodes, or we can set pos relative to something else. I should say set pos x, y, z. Yeah. So we pass in an optional node in the first parameter to set pos, followed by the relative position that we want it to set. It means we are going to set this node to its position relative to the node we specify. That is to say, if this node were directly apparented to this node, set its position to x, y, z, but actually set it to whatever position it would have to have in order to have that position where it is, which is kind of crazy. Another way to think about it is, after I call setPos render xyz, the next time I call getPos render, it's going to return xyz. So if I set pos relative to render, I'm setting his position in world space. No matter where he is in the scene graph, no matter what his parents are, no matter where his parents are transformed, I can set his world space position pretty easily. And furthermore, again, I can set his position relative to this node. So if this node represents some space, for instance, maybe there's a boat going by under the train tracks as the train passes over a bridge. Boat going by 90 degrees to the train. I can set my guy's position relative to that boat, even though he's actually on the train. I don't know why I want to do that.
Jumps out and lands on the boat.
Yeah. Well, if he jumps out and lands on the boat, Now we're talking about what reparent to. And this is, of course, we've got a reparent to operation. We could just take our node and parent him to the boat. And now he's a child of the boat, and he'll move along with the boat. But whatever position he had relative to the train, say he was standing at 050 on the top of the train deck, he's going to carry that position with him, and now it's going to be interpreted in the context of the boat, which might be a completely different place in world coordinates. So the basic reparent to operation does not change that pause. It takes it just to the new context and reinterprets it there. But there's a different operation called work reparent to, WRT reparent to. It stands for with respect to. And that's a clever thing where it reparents the node to its indicated target, but also recomputes its local transform so that it ends up in the same global coordinate space. And boy, that's doing a lot of fancy calculations. It has to go compute the relative transform first, then it has to go reapply it to adjust its transform. But again, Panda's trying to do its best to cache that, so it's not quite so bad. And we'll talk about the caching mechanisms in a little bit. Scene graph operations in a nutshell, right? Transforms, relative transforms, great operations. Everybody loves them. Questions so far?
How often can you do work reparent to before you get problems?
I've got a ringer in the audience. Excellent question. Yes, not too often. It depends on the nature of the problems that you're, well, okay, so the problem is, I mentioned earlier that the transform state, which contains each transform and stores component-wise the transforms that you stuff on it. The reason it stores component-wise is because once you encode these into a matrix and then break them out again, you lose some arithmetic precision. Particular rotation and scale, they get pretty badly corrupted by the conversion into a matrix and back again. So as long as you can store things just component-wise, you're pretty good. Unfortunately, once you do a work reparent to, you're going to cross over multiple transforms. Chances are pretty good it's not going to be able to do all those things component-wise, especially if you've got scales involved in there. So what it's going to do is automatically compose that into a 4x4 matrix, and then recompose it out to the components. And that means that you're going to have loss on precision in that work reparent to operation. So usually it's a few decimal points, places out past 0. It's not too bad. You might have been looking at 0 and 90, 0, looking at heading of 0 or pitch of 90 or something like that. At the end of the work reparent to operation, it might be 89.9999. Okay. As scale, typically scales where you start to see the problem even worse because scales and rotations are kind of bound together in the matrix. Your scale might have been 1 before you started it. After the operation, now it's 1.0001. Okay, it's pretty nearly the same thing. But you do the same operation back and forth a few hundred times, and suddenly you're looking at a scale of 1.1. And now you can start to see it. And these sorts of things really tend to accumulate quickly once they get snowballing. We've had a few errors where people were doing work reparent to without realizing it, across the scale without realizing it. And if you do that on the camera, boy, the whole world goes crazy. So yeah, work reparent to is a very powerful feature, but often misused, and it has to be used with respect. Thank you. Okay, I'm almost done with the basic stuff in scene graph. There's one more thing that's worth talking about, this fundamental scene graph stuff, which are the render attributes. These are used less often than the transforms, but they're still pretty important. And is one of the powerful things about Panda scene graph in particular. Render attributes are basically anything that affects the way the object, the geometry is actually rendered. This includes the color, the texture, the lighting, anything that affects render state in general is encoded in one of several different kinds of render attribute classes we've got in Panda. And normally you don't deal with the render attribute classes directly. They're hidden from you because they're kind of inconvenient and clunky to use, but they're stored internally on each Panda node. Just like we store a transform state on each node, we also store a render state object on each node. And most nodes just have a render state empty, which means it's got no particular attributes. But some nodes have a render state which has a list of attributes in it. So if we call node.setColor, for instance, which means we want to set it to, I don't know, 0, 0, 1, make it blue, that's going to create a render color attribute, or a color attribute object, and store it on the render state object in that node. And the render state objects accumulate very much like the transform states do. So that as we traverse the scene graph, we were, remember, building up the transforms as we go, composing the transforms so that by the time we reach a leaf, we apply that transform to the vertices. We're doing the same thing with the render state. As we traverse, if we come across a render state here which has a color attribute, a render state here which has a texture attribute, maybe a render state here which has a different color attribute, these all accumulate together into one big render state which finally gets applied to the vertices. This works almost identically to the way that transforms work. In fact, you can even do relative operations on the render state. There's not usually much call to do it, but you could say, what is my color relative to this guy over here? What is my color relative to the root? So if there's a set color on this node, and I'm down here on this node, I don't have any set colors on my node. If I call get color on this node, it's going to say, sorry, you don't have any color. But if I say get color relative to render, it's going to say, oh, well, you have whatever color this guy has, because it inherits all the colors down. And if I happen to have a set color here and a set color here, and I ask, what's my color relative to this guy? Well, it can unaccumulate this and reaccumulate that and give me the answer. It's kind of crazy. Most of the time, there's not much reason to do that. There are a few attributes that are particularly useful for that, and these are the things that are most similar to the transform state. For instance, color scale is something that you might want to accumulate over several nodes. And the texture matrix, which applies a transform to the texture coordinates, is something that you might want to calculate over several nodes. And that works in the way that you expect.
What operation is it using to accumulate? Is it doing a multiply, or?
It depends on the attrib.
You can change that then?
Particular attributes have different operations. For a color scale and a texture attrib, well, color scales multiply. When two color scales go together, they multiply. When two color attributes, when a color attribute is defined as completely replace the color as opposed to a color scale,
Okay.
when two color attributes go by, then the second one just wins. And that's the way that most of the attributes work. Most of the attributes, the second one wins. There are other kinds. A texture attribute has multiple textures within it, one texture per texture stage. So when two texture attributes combine, the second one wins unless they use different texture stages, in which case they combine into a multi-texture attribute.
Okay.
But yeah, different kinds of attributes have different ways of applying. Most of them just replace. Because attributes tend to replace, sometimes we, well, as I said, if I do a set color here and a set color here, the lower one will win. Sometimes that's not what we want. Sometimes we've got a color attribute down here on this node, but we want to say, never mind, I know you've got a color attribute, I want to have a different color and I mean it. And that's when we use a priority override. This is what the extra comma 1 is on the set texture call that you see on the Panda 3 website a lot. And that just means override any children. So if I call set texture blah de blah, the default override is 0 on any operation like this. And that means if I do a set texture here and a set texture here, and I'm not using multi-texture, then the second one will win. And commonly we load up a model from the model pool, or loader.load model, and it's already got a texture on it. If we want to change that texture, we just do if we do a set texture on the root of the model we loaded, it's not going to override because there's a lower level node inside the model we loaded that has a new texture on it. If we want to really change the texture, the easiest way to do that is with some comma override greater than 0. And typically we use 1 because 1 is greater than 0. But the official rule is, whatever number you specify here in this call is the priority of the new attribute that you're applying to the scene graph. And in general, a higher priority will replace any similar attributes in the lower nodes of equal or lesser priority. So if we then want to go back and on the top level scene graph, we want to have another set texture call that overshadows this one. Set texture 1 isn't going to do it. We're going to have to do set texture 2 to shadow set texture 1. And so on. So we don't often get to that level of complexity with these things. 1 is often enough, but sometimes somebody uses an override and we have to shadow with a higher number.
Composition rules don't apply. It overrides composition rules too,
Yeah,
right?
This is a bit of a clumsy hammer for this sort of thing. Set texture is, since it's a fancy attrib that has rules about composition, that is to say, if I have 2 different set textures at the same level with both comma 0 or unspecified, and they're using different texture stages, then they'll combine together into one multi-texture attrib. And often that's what I want. If I do a set texture comma 1, this is going to completely replace anything below me, and it will no longer combine. So it does get a little difficult to use set texture with an override in conjunction with multi-texture. It means that if I want to use set texture with multi-texture, anything below it that I want to combine with this had better have the same override. Does that make sense? Set texture is the only funny one in that way, because most of the other attribs don't have this composition that set texture does. Most of them are built to replace, set color, just built to replace anyway.
Just to make sure I understand really quick, you said that overriding happens when the higher level is less than, is greater than or equal, or is it only when it's greater than?
Greater than.
Okay.
So normally a lower level node will replace the attribute or combine with the attribute from its parent if its priority is less than or equal to.
Okay, so if I had a set texture 1 and the parent also had a set texture 1, then you would...
Oh wait, I said it wrong. But yes, if you have a set texture 1 here and a child also has a set texture 1, then they will combine naturally.
Okay, and that's okay. So it's the same thing, basically having the same priority as if you were both set to 0 and you were never dealing with
Right.
the issue at all. Okay.
In fact, the particular value means nothing. Panda just happens to use 0 as the default value.
Right.
You can use negative values. You can use positive values.
Okay.
And Panda doesn't care about that. It just cares about the relative value. Okay. There is an operation on node path. You can recursively change all the children below that node path. You can add an increment to all of its overrides. We sometimes do this when we load a model from disk. We want to bump its overrides down by 1 so that we can easily set texture things. But that's not often done. Okay. The call, we have a whole suite of calls that operate on the various kinds of attributes. Set texture, set color, I've mentioned a few of them. There are more attributes than we have convenience functions for this point, this purpose. And it's just because, we got 20, 30 different attributes and we had to write a method accessor for each one of these. We just got crazy. I mean, NodePath already has some 200 methods on it. For the lesser used attributes, you have to just create an attribute by hand. Let me think of an example of a lesser used attribute, like
Color blending?
Character join effect.
Sorry?
What about color blending?
Color blending. Yeah, that's a good one. We don't have a set blend. So if you want to create a color blend, you have to call set attribute and create a color blend attribute on the fly. And there's a bunch of parameters in there. Every attribute has a basic constructor that you can construct in Python and pass it whatever kind of crazy parameters it wants. And you can always do this for all the kinds of attributes you want. But for many of them, we just have a convenience function, which is much easier to use.
Isn't most of those attributes aren't constructor? You have to do a special function though,
Oh,
right?
you're right. You can't construct the attributes directly. The actual operation would be colorblend attrib.make. And that has some funny parameters. You're right, good call. And the reason that you can't construct the attributes directly has to do with the way that Panda caches all these things. And I'll talk about that reason when I get to caching. Swell. Okay. There's just one other fancy thing that Panda does with the scene graph. And I've alluded to this already, and that's the recomputation of the bounding volumes. Whenever you do any operations that change the position in space of an object, or its size, or some property of the spatial property of the object, Panda has to automatically compute the bounding volume of the object. And it does this for rendering optimizations. It's helpful for Panda to know, when it reaches a node, roughly how big is that node? How big is the geometry to be rendered within this node? And that includes all the geom nodes at this node and below. This has to do with view-frustum culling. If you're familiar with the algorithm, when we're looking at a scene, say we're looking from the top down, there's lots of things in the scene. Lots of things we might be looking at. Some of the things are completely outside of our view-frustum. There's no point in even rendering those nodes. No point in even visiting those nodes. Some of the things are completely within the view-frustum, and some things are intersecting the view-frustum. So when Panda traverses a scene graph, it doesn't actually visit every node in the graph for the purposes of rendering. Each time it visits a node, it checks the bounding volume of that node and checks to see if the bounding volume is within the view-frustum. If the bounding volume is completely outside of the view-frustum, it stops right there. It doesn't go any further. If the bounding volume is completely within the view-frustum, then it continues to traverse a node, and furthermore, it doesn't check any more bounding volumes, because it knows that everything from that point on is going to be within the viewing frustum. And if the bounding volume happens to intersect the view frustum, then it's going to continue to render, and every node thereon is going to continue to check the bounding volume. So it's important that Panda knows what the bounding volume is of each node. This is a real important optimization. It helps a lot for rendering, especially because you can imagine there's things all over the world, and you're really only looking at a tiny little piece of the world at any given time. So this just throws out lots of stuff right off the bat. It saves a whole lot of time. But it means that we need to know some kind of volume that is larger, or at least not smaller, than any of the geometry in this, at this node and below. Panda uses an algorithm to generate these bounding volumes, which is not particularly tight. It will generate fairly loose bounding volumes. The volume it generates might be much larger than the geometry it encloses, but it generates these in such a way that it's relatively quick to compute them. And that's a fairly good trade-off. Although if we got a tighter bounding volume that actually completely enclosed the vertices and went no further, we'd have a fairly accurate test here, and that would help. But we'd spend so much time computing the bounding volumes, it wouldn't be worth it. So on any node, you can call getBounds, and that will tell you what Panda thinks its bounding volume is. It will be a loose bounding volume. By default, the bounding volume is a bounding sphere most of the time. There are other kinds of bounding volumes. You can put Panda in a mode where it computes bounding cubes, bounding rectangles rather, where you get a min-max, etc. So a lot of times you got to be careful with writing code that just does a getBounds and then immediately calls getRadius on it, because it's possible if you're running Panda in some funny mode, it might not be a sphere, in which case getRadius is going to fail. You can call getBounds on any node, and that's going to compute the bounding volume around all the children below it, including any transforms on the children. So if my node is made up of multiple pieces and I change a transform on one of the children to move that piece further away, the bounding volume has to get larger to include that. Furthermore, if I add a new child onto a node, the bounding volume might have to get larger to include that. On the other hand, if I take nodes away, the bounding volume might be able to get smaller. So any of these operations where I change a parent or I change a transform of a node is going to affect the bounding volume. Panda has a lazy algorithm that computes the bounding volume. Rather than compute bounding volumes as soon as you ask for them, which would get quite expensive, and also rather than recomputing bounding volumes every time you make a change, which could get expensive, what it does is as soon as you make a change that would invalidate the bounding volume, it just marks it invalid, and also marks all the parent bounding volumes invalid all the way up to the root. And then if I make a change down here to this node that makes it invalid, I mark this one valid and mark this one invalid. And then I get to here, I see this one's already been marked invalid, and I can stop there. This way, so making lots of changes to the same node, I don't do a lot of recomputation. It saves a lot of time. First time I ask for a node at the bounding volume, I only have to check to see this invalid flag. If I see that it's invalid, then I can recompute the bounding volume on right there. And I recompute the bounding volume and all its children recursively, and I've got my answer. I don't have to propagate upwards until I ask for the bounding volume up here. This works out pretty well. There are times when it goes wrong. One classic example is always biting people is the character animation. When we do character animation, it's a special case, because usually we're not animating the nodes. The character animation system actually works on the vertices itself. Now, it would be possible for the character animation system to, every time it computes an animation frame, to examine all the vertices and figure out where the new bounding volume is. Of course, that would be expensive. So we don't do that. We just take the tedious way out and ignore it completely. We compute the bounding volume when the model is loaded. First ask for the bounding volume. That's the bounding volume it is. We assume that the animation is not going to substantially change the bounding volume. And that's true as long as your animation is fairly contained. If you've got a character walking in place or reaching for something, he's not usually going to change his bounding volume that much. And so it generally works. But sometimes you use your animation system to really radically change an object's position. For instance, you might animate a guy jumping and landing again, and then he's completely leaving his bounding volume and coming back in. And that could cause problems. Effectively, when this happens, you'll be running the game or whatever, and your guy will maybe just disappear because he's animated out of his bounding volume. The bounding volume is no longer in frame, but he is. But Panda doesn't really realize that, and he thinks he's still in frame because his bounding volume is still in frame. And that's an unfortunate problem. There's a few workarounds for that. One day we'd like to fix it. We'd like to fix it by pre-computing the bounding volumes for the animations. We can do this. We've got, we've done this before. We just don't have a place to do it right now. We'd have to store the bounding volumes in the animation table. It's on the list of things to do. In the meantime, what you have to do is, when this situation happens, you have to go in by hand and set a bounding volume that you know is large enough to include all the animation. Sometimes, for simple cases, you can just give the object the omni-bounding volume, which is a special bounding volume which is infinite. That means never call this guy, he's always on frame. I don't care where you think his bounding volume is. Of course, you wouldn't want to do that for any complex scene, because if you start putting omni-bounding volumes on all these things in your complex scene, well, they're going to get rendered all the time, even if they're far behind you. Okay. It's fun. Questions about bounding volumes and other stuff? There's one other thing we can do, which we do sometimes. I mentioned this. You can do set bounds on a node. When you call set bounds, you can arbitrarily set a bounding volume of your design. But what this really means is give this node this bounding volume and accumulate it as well as all of its children. So if I set a bounding volume on this node, and the node still has children, the reported bounding volume is going to be the sum of my bounding volume and all of its children's bounding volume. There's no way to replace arbitrarily the bounding volume without inheriting up from its children. Usually you wouldn't want to do that. I guess you could go down to all of its children and replace them too. Yeah.
Question.
Yes.
So let's say you set bounds on a node, and then later on, another node gets parented under that node.
Mm-hmm.
So does that mean the bounds that you set could potentially be lost because a new node got put in there?
Well, the bounds that you set is still there. But when Panda traverses, or when you call it get bounds, it's going to return the sum of your bounds and the child node. If you then take that child out, it'll return back your original bound.
Okay.
So it still remembers the bound that you set,
Okay.
but it is not, when you call get bounds, it doesn't actually return the bound that you set. It returns the bounds plus all of its children bounds.
So that's the external versus internal
Yeah,
bounds?
that's
Okay.
right. You're setting the internal bounds, and when you call get bounds, it's actually returning the external bounds.
Quick question for clarification.
Yes.
You said that if we had someone far behind the viewer who was set to the omni-bounding volume so that he would always appear, you said that he would get rendered. Just to make sure, wouldn't he still be getting clipped once you're actually passed off to, once you leave Panda and are passed to the video card itself?
Yes, that's
Okay, so that, basically by rendered, you mean Panda is passing vertices to the card, but he's not necessarily appearing on screen.
yes, that's
okay.
right.
Cool.
A good clarification.
You lose significant savings, but you're still not getting visual errors, is just what I wanted to make
Yes,
sure of.
that's right.
Okay, thanks.
All right. I guess it's time to talk about caching. Okay, so I've alluded to this mysterious caching that Panda does. If you ask the getNet transform of a particular node once, it's going to compute that. If you ask it twice, it's not going to compute it. It's just going to return the cached answer. That's a very handy thing. But there are some real problems with solving this. I mean, the first naive approach to doing that is, here, let me draw this a little saner again. The first thing you might want to do when implementing caching is say, every time I compute a net transform of a node, store that net transform in the node so for the next time I compute it. That works great until you have instancing. Suppose I have instancing where this node now has two parents. That means it's inherited one transform from this guy and a completely different transform from this guy. So the net transform has two different answers according to which instance I'm looking at. How am I going to store that in the node? Suppose I've got thousands of parents. How am I going to store them? It's possible. I just said we could have a flight simulator, remember, with thousands of trees. So there's one tree that gets instanced thousands of times. So yeah, and each tree would have its own location. So yeah, obviously I can't store the transform state cache in the node itself. I don't know. What we finally decided to do was store them in the transform state objects. So what we do is the transform state object has a cache of all the transform state objects that have been composed with me. So let's see. Inside a transform state, we've got a matrix, basically, a 4x4 matrix. And we've also got pause, hyper, scale, and other stuff. And we also have this cache. And if you create a transform state, you'll see the cache. The cache is it's a hash table. And it's got a hash table of other transform state objects, which are stored by pointer. So if I take transform state A and compose it with transform state B, let's draw transform state B. A compose B. If the first thing I do is take B and look it up in A's cache. If B shows up in the hash table, swell, I've got the answer. If B is not in the hash table, then I have to compute the result on the fly and then stuff it in the hash table. Next time I ask for A compose B, I've got the answer. It's already in the hash table. Now how does that work in the scene graph traverser? Well, if I got a transform here, and a transform here, let's call that A, B, C. So I take A compose B, and gives me a new answer, which will be a new transform state. Let's say B is not in A's cache, so I have to go ahead and compose them on the fly. So I compute A compose B, and then result is some new transform state, which will be D. So A plus B gives me D. Now I'm going to take D, which is the result of AB, and compose it with C, as I'm traversing the scene graph. Decompose C. And now, again, C is not in D's cache, because D is brand new. So I'm going to compute decompose C and return E. And here's the answer for the net state of GN, right down here. Next time I do this, I still get A up here. I compute A compose B. I look in the cache, look, there's D. Come down here, decompose C, look in the cache, look, there's E. Perfect, right? The only trouble is, well, I mean, it's kind of unfortunate that we still have to actually traverse the graph in order to get that answer. It'd be nice if we could just look in the node and say, here's your answer. But, just a scene graph, deal with it. And in fact, it turns out not to be too terribly expensive to do that cache. Because you're only just walking pointers. You're traversing, maybe 5 or 6 pointers, big deal. If your scene graph is thousands of levels deep, you got bigger problems. But fortunately, we don't have to recompute matrices. And that's especially big when we're doing the inverse matrix, because we also have, in the transform state, the inverse cache, which works similarly, except it includes the concept of having inverted this matrix first, which we do often in this word operation. We're going across the root, we invert the matrix. And the matrix inverse is actually a really expensive operation, so it's really nice to be able to cache that. Now, the problem with the cache, as I've described it, is how do you let go of it? empty this cache, right? If just as it is, you're going to accumulate these things forever. Eventually, you're going to fill up your memory, and you're going to crash and burn. Fortunately, the transform states are all reference counted. So we have a reference counting algorithm. We know the algorithm we use is once the result of the cache gets destructed because it no longer has any references outside of the cache itself, it automatically removes itself from the cache. And it can do this because in the result of the cache, we store another pointer back to A. So here's my example of A and B. We've got A, which has a pointer to B, and B, which has a pointer to A, and they both store each other in their cache. So if A destructs, it removes itself from B's cache, and if B destructs, it removes itself from A's cache. And now, this means that as long as I've got a pointer to either A or B, actually, as long as I've got a pointer to both A and B, and both A and B still exist, then D will continue to exist, because I might actually want to multiply them again someday. If either A or B goes away, and there are no longer any references to this particular transform, A or B, then D will go away, because obviously I'm never going to want to multiply those two transforms again. This magic still requires one fundamental principle, which is that these transform states aren't going to change. I store them in the hash table by pointer. That means, and I'm doing a lookup by pointer. That means I've cached the result by pointer. If a transform state later changes, that's invalidated the cache result. Intolerable. So we just assert transform states never change. Sorry, every transform state is constant. If you want to change a transform state, what you should do is create a brand new transform state that's got the new value and replace the existing transform state that you had before. And that actually works out pretty well with this reference counting rule too. So if, for instance, I change the transform on this node to some other position, then it's going to create a new transform state, completely replacing the transform state B. Let's call it, F. So we just store transform state F on this node. And if there are no other transform states anywhere in the world that happen to be the same as B, then B now, reference count goes to 0, and it gets deallocated. That means D gets deallocated, and C stays the same, but E gets deallocated. Everything propagates out of the scene graph. And look at that, isn't it great? Now we're not wasting memory anymore. It can go wrong. This whole system can go horribly wrong. Biggest problem is what happens if A composed B produces D, which composed C, which produces E, and maybe E is actually the same thing as A. If that happens, we've got a cycle in the reference counts. And oh, well, gosh, these are never going to go away. Well, we've tried different approaches to solving that particular problem. One approach is to let E be a different pointer than A, even though it's actually the same value. That works okay, but it tends to cause more objects to fill up in the cache, and you get less cache repeats. Another approach is every time we remove a node, we do a quick traversal, or from time to time we do a quick traversal over a cache list and look for cycles. It's kind of a garbage collection algorithm. That works okay too, but it's garbage collection. So every once in a while you pay this hit for garbage collection, which is kind of lame. We haven't found a great solution that works in all cases, but fortunately it doesn't come up that often. I think most of the time, right now the default behavior is a combination of what I described. We minimize the number of times that a computed result is shared pointer with the existing result, and we also do an occasional garbage collection on it. Did I go over that pretty clearly to everybody's satisfaction?
Question.
Yes?
So if the node pointed to by the C transform state, if that node is stashed, E becomes invalidated?
Well, if the node is stashed, it keeps its transform.
Okay.
So E would still be valid and C would still be valid.
Okay.
But if I change a transform, or if the node gets destructed, then we'll take its transform with it, and then E would be deallocated also.
Okay.
So there is a similar bit of magic that happens with the render state. Basically the same algorithm. Render state, I mentioned, is just like a transform state in many ways. Render state is fundamentally a list of render attributes. And it works the same way. The render state has a cache and another cache, and each has a hash table to the other thing. So when you combine render states by traversing the scene graph, render state A, render state B, compose, stores that result. So this is helpful for traversing the scene graph quickly without having to recompose all these render states every time. Same rule applies though. Render states therefore have to be const. This also means, since a render state is basically a list of render attrib pointers, all the render attribs also have to be const. And this is why you can't just create a render attrib on the fly, because if you call the constructor of a render attrib, you've created a non-const render attrib, which is not allowed. That's why all of the render attribs have the make function, which is designed to create a render attrib of the appropriate type with the appropriate parameters and return that const attrib to you. Once you've got it, you can no longer modify it. You can create a new one with new properties. Some of our render attribs, which have things that you want to build up with complicated ways, like a texture attrib, for instance, might have several textures on it. It's kind of clumsy to pass all those textures into the texture attrib constructor. So we have a multiple-step process to create a texture attrib if you've got multiple textures involved. You create a texture attrib once which has the first texture that you want, and then you use that texture attrib that you got, to create a new texture attrib that has a composition of two textures that you want. And you keep doing that until you've got all the textures in it. It's a little clumsy. It means you're creating and destroying several texture attribs in the process of creating one. But it's not actually that bad. We do some subtle tricks with the new and delete operators inside Panda to make it so that the allocation and destruction of these objects is really very quick. Because we never actually deallocate them, we just put them on the free chain. And next time you want to get one, we pull off the free chain first. Common things to do to improve performance at the low level. So it means you don't have to be too worried about creating and destroying lots of render attribs and render states and transform states. It doesn't work all the time. There are times when something that you think should be a relatively simple operation, like just doing set color on a node, seems to be taking milliseconds for some reason. For instance, maybe I just do set color on render. That shouldn't be so bad, right? But then it turns out, as we're traversing, I've just invalidated every darn render state down the tree. I've got to recompute all those caches, destroy a bunch of things, maybe do some garbage collection on the way. And yeah, it adds up. Yeah, sorry.
Is that why time of day stuff is having issues potentially?
It might be. It might be.